Okay, so in this theorem, we're going to show that the property of being a domain is sort of passed on to the polynomial ring. So if you have any ring, you can always consider polynomials over that ring, and in this case, a single variable. But we'll see actually that um, this will tell us that it's true for an arbitrary number of variables. And one can ask what kind of properties in R pass on to those in R adjoin X. And being a domain is one of those properties that passes on. There's an easy direction here and a hard direction. I think the easy direction is the reverse direction. So we're going to go ahead and suppose that R adjoin X is a domain. We can view R as a subring of R adjoin X via constant polynomials. Then R is a subring of a domain, and so it's a domain. By the theorem we proved previously. Okay, the harder direction is the forward direction. So suppose R is a domain. Well, then in particular, R is not 0. So R adjoin X is also not 0, as it contains R. So it's a non-zero ring. And we saw already that that being commutative is a property that passes on to the polynomial ring. So R adjoin X is also commutative. And so the only thing that we need to check is that R adjoin X does not have zero divisors. So now that we've sort of gone through the the really definition heavy construction of polynomials, we're going to be a little bit more fast and loose with multiplying them together. So I'm not going to be very precise with when I'm extending by 0 and the products and so on. We're just going to remember that polynomial multiplication is just the distributive property, then you collect like terms. Okay, so suppose that to show that there's no zero divisors, we have two polynomials. And they are non-constant. Well, at least one is non-constant. Okay, let's not go there. Let's just say suppose we have two polynomials. We can write them as a1x plus amx to the m, and g of x as b0 plus b1x plus bn x to the n, with am and bn the leading coefficients. They're leading coefficients, so they're not 0. And then f times g has leading coefficient am times bn, which is non-zero because R is a domain. And this is the product of two non-zero elements, right? Two non-zero elements in a domain, it remains non-zero. Okay, so the property of being a polynomial ring, so the property of being a domain passes on to the polynomial ring. Now, a corollary of this is that's worth writing down just to have it written down, although it's not really, it's not really worth proving, but you can sit here and write down a quick proof of it if you want. It's if f is a field, then polynomials over f is a domain. Of course, the reason is all fields are domains, and we just proved that if polynomials over a domain are in fact a domain. Another corollary of the proof of this is that if f and g are polynomials with coefficients in R, and R is a domain, then the degree of f times g is equal to, well, let's go up real quick. So f was degree m, g was degree n, and the product has degree m plus n. So the degree of the product is m plus n. This is called the degree being multiplicative or additive. The words get kind of interchanged sometimes. And let me point out that this is not true when R is not a domain. So just as a last example, so in, for example, Z4 adjoin X, we have 2x times, I don't know, let's make this other one a little bit different, 2x plus 2. So these are positive degree terms, right? If this is our f and this is our g, they both have degree 2, or degree 1. So degree of f is the degree of g is 1. But their product is 4x squared plus 4x is identically 0. The degree of the zeroid polynomial, let me just say degree of fg in this case, is the degree of 0, and the degree of 0, the 0 polynomial is regarded as negative infinity. In particular, it is not equal to 1 plus 1, which is the sum of the degrees of f and g. So you really, really, really need a domain for this to be true. Otherwise, the degree fails to be additive.